everything came into creation in the gap between fire and ice. The world tree, Yggdrasil, connects the 9 worlds, including Asgard, home of the Aesir, the Norse gods, and Helheim, or simply Hel, the underworld, where the dead go. And there is Valhalla, the hall of the honored dead, a majestic, enormous hall ruled over by Odin himself. Those who die in battle, if judged worthy, are carried to Valhalla by the Valkyries. In Valhalla, these warriors join those who have died in combat, the Einherjar, and legendary heroes and kings in preparation to aid Odin during Ragnarok, the twilight of the gods. In Ragnarok, Odin will fight the wolf Fenrir, and Thor will fight the serpent Jormungand. Jormungand surrounds Midgard, the middle realm where humans live. And Thor will fight valiantly, and Thor will win. He will kill the serpent, but the serpent's poison will kill Thor in the end as well. The 9 worlds and Yggdrasil. Asgard, home of the Aesir. Midgard, home of humans. Helheim, home of Hel and the dishonorable dead. And many more worlds. The Vanir, the Light Elves, the Giants. But aside from my obvious interest in the subject, why are we talking about the Norse? Well, today our goal is to examine some useful tools for analyzing and fixing problems in your program. We are going to learn about Valgrind and Helgrind, and it would do you well to pronounce them correctly. The endings are pronounced grind and not grind. Where do they take their names from? Valgrind is the gateway to Valhalla, a gate that only the worthy may pass. Helgrind is the gateway to Hell. So, is your program worthy? These are analysis tools for your C and C++ programs. They can be applied to other things as well. And they are terrible for performance, but they're wonderful for finding errors in your program. And so, to use them, we will start the tool of our choice and tell it what program we want to run and observe. The target program runs under the supervision of the tool that we've chosen, and then this does result in running dramatically slower than normal, but we get checks and monitoring of the program, and we can get some useful information out of that if debugging symbols in our compile are enabled, particularly if you want stack trace to be useful. Now, this lecture is unlike the others that we have seen so far, as though that were not obvious, in that it mostly involves actual demonstration as opposed to content in the notes or the slides. Now, given that this is a video, doesn't really make much difference to you, I don't think. But if, of course, this were being held in a lecture hall, this would be one that you would not want to miss as a result of the fact that the demos just wouldn't happen again. Now, we will not have time for absolutely everything that is interesting about how to use Valgrind and how to use Helgrind, so you'll have to play around with it yourself. Fortunately, there is an exercise for this, which gives you some experience with it. And truly, you should be an expert in it, or at least competent in it, when this course is done, because from here on out, we will expect you to use it on your programs. We will. We will check. Did you leak memory? Do you have concurrency problems? Now that you know, you got to use it. Be brave. Be valiant. See you on the field of battle at Ragnarok. Now, Valgrind is the base name of the project, and by default, it will run the memcheck tool. And memcheck is supposed to find errors when you interact with memory, and there are a few different categories of that, but at the highest level you could think of ways you interact with memory as being when memory is allocated and deallocated, but also reads and writes are observed. And so memcheck will validate every memory access and every allocation and every deallocation. So if you think for a minute about maybe what are some of the things that it could find, do any ideas sort of come to your mind about that? Some are reasonably straightforward. If it tracks allocations and deallocations, it can and will find situations where you have failed to deallocate memory. So that one is straightforward. So memory leak, good. But there are other things related to reads and writes. If you access uninitialized memory, it'll tell you. It'll say this was never assigned a value, and then you tried to read it. So, okay, good. Reading off the end of an array, if it can tell how big a memory allocation is, it knows the size of the array, and if you were writing or reading beyond the end of the array, it knows that that's a problem. So, yep, that will be reported. Incorrect freeing of memory, so double free or something like that, or a mismatch in free calls. Double free usually crashes our program straight away, so we're not worried that we're not going to find it. But nevertheless, that doesn't necessarily happen. Double free might happen commonly, but there's no rule that says it must, so knowing about it is valuable. And there's a couple other things that it can check on. Incorrect use of some standard functions like memcopy, because these are common patterns, so it's possible to check and see, is this doing what it is supposed to do? And it can also check for using memory after it's been freed. This on its own is a whole big category of problems, well, I mean, no program is really immune from them. There was in March 2019 a well-documented situation where a Chrome vulnerability occurred because it was a use after free bug. So that is, after the memory was freed, then there was some access to that memory, which shouldn't happen, but it did anyway. And thing is, I mean, this was Chrome, so it's not as though there was a lack of resources to do this. So I can't say that this was a problem where Google just didn't have smart people either. It's just the nature of the language. The other thing that it can check for is if you ask for an invalid number of bytes in an allocation. So if you have an allocation that isn't a fixed amount, it's not size of int or something, some fixed value times size of int. It's a multiplication based on some user input value or something. In principle, you could come up with a negative number, and that would be reported as an error in this case. Now, errors will be reported to the console, as we'll see when we analyze one of our programs here in the command line, only when they occur. Only when they occur. So that's important. We don't have a guarantee that everything in your program is correct. All that Valgrind can do is report on errors that it sees. So let's get started with a simple example. We'll run this on program workers. All right, how did we do? We did not necessarily get the ideal outcome, because, well, what happened in this program? We start Valgrind, it tells you it's running the memcheck tool, and then there's some output from the program. It's about searching an array, so it's not super interesting in that regard. But heap summary, in use at exit, 1,638 bytes in 4 blocks, and there were 18 allocations and 4 frees, and that's not good. That's not good. The leak summary gives you a breakdown. So it tells you what memory was definitely lost, indirectly lost, possibly lost, and still reachable. So we have to talk about sort of what each of those mean before we dig into our actual program. But the first thing we'll do is we'll actually take the suggestion here and we will use the option leak check equals full to get more details. Okay, again, to get even more details, we'll take the next suggestion, which is show leak kinds equals all. And, well, we got a lot more output to read through, but we have to, like, try hard to interpret this. Okay, so let's talk about what the different kinds of leaks are. So definitely lost is Valgrind is completely sure that this is a memory leak. You should fix it. I'll show you a memory leak later on so we can see how it's reported and we know how to fix it. And that will be, I won't say easy, but I'll say straightforward. That it is usually not too difficult to track down some information about what's gone wrong. Devising the fix can be a little more complicated, but we can do it. It won't be impossible. Indirectly lost. This is usually a problem with a pointer-based structure. So you have a linked list and you lose a reference to the head of the linked list, and then there are all the remaining nodes in the list that, there's pointers to them and everything, and that is indirectly lost. The head of the list is lost, but the rest are indirectly lost. And if we resolve problems with that, we do so by fixing the definitely lost, and usually that is enough to clear up the indirectly lost stuff. Possibly lost, Valgrind is not sure. It thinks that something is wrong, but it can't prove it. You can trick Valgrind a bit by doing weird things where you have like a pointer in the middle of an array. If you don't have the pointer pointing at the beginning of the array, Valgrind can get kind of weirded out by that, so it could appear as possibly lost. Still reachable. So this is memory that was still allocated and it could have been freed, but at the time of the program exit, there still exist valid pointers to it. So you can still get to the memory. It isn't lost, it hasn't been leaked, but it didn't get deallocated either. And so there are also suppressed. Far beyond what we want to talk about in this course, you can configure the tool to ignore things, and if you say, I want to ignore this particular thing, then it will allow you to just have it count in the suppressed column, and it doesn't hassle you about things that you have said, actually this is fine, it's a false positive, or something that you need to ignore. Okay, let's look at our output here. Thing is, we have a whole bunch of output. Maybe we'll start with a simpler case first. And what I'll do here is just comment out this free statement. So I am not very good at my C programming assignment, and I fail to deallocate this memory return value here at line 42. Okay, let's try that. And we will run it with Valgrind. And, okay, we have all of the things that we saw before, but also we have a definitely lost amount. In fact, 16 bytes in 4 blocks. So a total of 16 bytes are lost, and there are 4 allocations that make up that 16 bytes. Now, you're not guaranteed that it's divided evenly, but it is a good hint that that is the case. And what you will see immediately following that is where the memory was allocated. So it was allocated by a call to malloc. Unsurprising. That's generally how we do it. And then it tells you search is the name of the function where this occurred, and it happened in the file workers.c. And there we have it. We have a line number which tells us where the memory was allocated. So let's go look at workers.c at line 50. Yeah, so the memory is allocated here, but it doesn't tell us where it should be deallocated. I mean, we know that it's deallocated in line 42, but that's because I have deleted or commented out the line that deallocated this memory. But unfortunately, Valgrind can't tell you where memory is supposed to be deallocated. All it can tell you is where the memory was allocated, and then you have to trace the path that the memory takes to try to figure out where an appropriate place for deallocation is. And so we'll see result is initialized here, and it's used here, and result is actually returned using pthread exit. Okay, sounds good. And where does the return value from pthread exit go? Well, it goes to pthread join. So the memory that was allocated on line 50 for a given thread, remember there's more than one, is passed using pthread exit, collected via pthread join, and pthread join updates the pointer return value, which is here on line 38, cast to RV. And then if RV is not -1, we print it out, and then this is the point where we no longer need that memory, so we can deallocate it. And you can deallocate it by freeing return value or RV. They both point to the same thing. So that is perfectly fine. So that is a good place at which to deallocate this memory. We've traced it for its lifetime, and we have made a determination that we no longer need it. So let's get rid of it. So we do. And that's how we know that we should put free return value here. But Valgrind can't tell you that specifically. All it can say is, well, there should be a deallocation, but it didn't get to one. Okay, let's look at the rest of the reported things here. So we have 36 bytes in one block, still reachable in lost record 2 of 5. It occurs at a malloc, which takes place here in this library, memcheck AMD64 Linux.sharedObject in the string duplication function at line 42, and load cache, lookup, map object, open worker, catch exception, open, DL, open, all that. So what we did with the first error that we saw is we got like a stack trace, and you might be sick to death of stack traces if you've programmed in languages like Java, but it is a stack trace, and it tells us how did we get to where we are. So that's okay. We're going to look through there, and we'll try to find the line of code that's ours. So I mean, we didn't write the implementation of malloc, so no big deal, but we did write search, and it so happens that's the second line. Now, you might have to search a little bit farther for some context, but that's sufficient. For the second error record, there is nothing in this that is any code that we wrote. So now what? Well, it's important for us to learn and understand what to ignore, or at the very least, what is out of our hands. This stack trace points us at the cause of the problem, but there's nothing that we did wrong in this case. It is a bug in a library, and you can't fix the library. So, I mean, just because something is in a library, I'll point out, doesn't mean you can just throw up your hands and say, well, never mind. Because sometimes if it's allocated in the library, there is a cleanup function, for curl. There's curl global cleanup, and if you leave that out, you could end up with a memory leak due to something that's allocated in curl because you didn't call cleanup. That would be a library call, but you could do something about it. You could do something about that. So, you should, and therefore, I wouldn't consider it okay for you to just ignore it and say, oh yeah, it's fine, in the library, can't do anything. For this particular issue, this is a known issue, and we can actually solve this. because in the library, it, as I say, is a known issue, and if you search for this, you can find a fix. So in that case, it's not unreasonable to want to fix that, although you could leave it alone. And the fix is actually pthread exit does not work correctly on this version of Ubuntu at this time. It's entirely possible that at the time when you want to run this, it's been fixed because there's been some OS update or some library has been fixed. But if you use return at the end of a pthread instead, and we compile that, then we will find that actually this will go away. All right. So, yeah, I wish I could tell you, that there is like a clear yes or no about whether or not a problem can be fixed or should be addressed. Unfortunately, you have to use your judgment on a case-by-case basis. That's unfortunate, but software is complex, and we got to do what we got to do. So anyway, what we have here is the dream. All heap blocks were freed, no leaks are possible. Like, gold star, pin a medal on me. This is the dream. Everything going that perfectly is unlikely in anything other than a small program. The workers program that we're looking at is functionally tiny, so it's very straightforward to make sure there's no library calls that don't do bad things, or if there is one, we can fix it. That's not necessarily realistic in every kind of program. I mean, ultimately, the more complex your program is, the harder it will be to get to this all heap blocks were freed kind of thing. But it's still the goal. You still want to try to get there if you can. Okay, now you'll notice that I compiled with the option for debug symbols, -G option. Ultimately, if you leave that off, as we'll just demonstrate briefly here, you will find that the error messages are less helpful. Yeah, so like here, all we got was a function name. Now it's a different leak, so it's a little different from the one we had before. But I didn't get a breakdown of what line it is in the function or anything else. It's somewhere in main. Now maybe, again, because this is a simple program, it's not too difficult to figure out exactly where in main something has gone wrong. However, for a sufficiently complex program, you could have a pretty big function, and it would be hard to figure out, or the function behaves differently depending on the arguments that it's called with or where it's called from, and that would be harder to figure out when all you have is the function that it appeared in. So if we do this again with the debug symbols, nope, I have to put the arguments in the correct order, otherwise these things do not do what they are supposed to do. And then we have more helpful information, whereas before it didn't really even tell you the file that it was in. I mean, we know where main is. That's easy. It's a one-file program. Fine. But now we have the source file and the line, which will really help you with tracking down some errors. So now we're going to examine a different program. This one was contributed by Professor Morton, and it contains a number of different kinds of errors, so you can see what those look like and how we deal with them. Nope, we don't need that. Leak check. Full show leak. All. Okay, so some things went okay and some did not. So what can we start with? So invalid read of size 1. This indicates that we were trying to access some memory that doesn't belong to us. Looking at the address 0x0 hex number 0, this indicates it is a pointer that's pointing to null, and we have a segmentation fault. Unsurprising that the next thing that happens is process terminating with signal 11, sig-v, segmentation fault, which happened when we were trying to parse this. Why? Well, it'll help if we look at the code. But if we go to main, so main is expecting some argument for n. I didn't provide one, and because I didn't provide one, we ended up with a segmentation fault. Valgrind is good, actually, at helping you track down where segmentation faults occur, so that's going to be helpful on most occasions. Sometimes, however, you will find that if you run your program without Valgrind, you get a segmentation fault, and if you run it under Valgrind, the seg fault doesn't happen. Why? Well, you see, when Valgrind is supervising you and watching, unless you are actually trying to read from this pointer that's pointing to null, sometimes if you do something like read off the end of an array or read an uninitialized variable or something like that, or use after free, Valgrind will note that down and it will say, oh, that wasn't cool, but it doesn't crash your program because you didn't actually read memory that belonged to somebody else or that the operating system said no to. So let's try again. And this time provide a number. Okay, how'd we do? Well, we have an invalid write of size 4, and we can start with there, and we also have a leak. So there are 6,000 bytes that are leaked. There were 1,501 allocations, 1,500 frees, yet we still somehow lost 6,000 bytes. So let's take a look. And we'll start with the first one. So at line 56, while I++ less than n, a at index I is assigned I. Okay. So like what went wrong here? Go back to the error. So it's an invalid write of size 4. Address is 0 bytes after a block of 6,000. And of course, if we deallocate here, this will work. This will solve our second problem. Okay, what's wrong? Why don't we update this with some additional output? Maybe that helps. Need to include the header. Oh, that's funny. Remove is a reserved name because it belongs in a different function, so we'll just replace that here. That will work. And let's run it with Valgrind again. Okay, so yeah, I print out all the I values. I mean, it would be just as easy if I made I 10. For the purposes of this, we get an invalid write of size 4. Why? Because we wrote off the end of the array. You probably figured that out. Why? Well, Okay, so like what went wrong here? Well, we wrote off the end of the array because this I++ less than n condition does something clever while we're modifying I in here with the postfix operator. And it ultimately means that array at index of n gets written to, but that is of course an off by 1 error, because we should expect actually to for the array to go from index 0 to n minus 1, and that's not the behavior that happens. If we uncomment here another line, we can observe a different kind of problem. We'll compile that. And again, we still have our invalid write here, but we have, again, a memory leak here at line 55. But also, we get an invalid read here on remove node, and an invalid read here, an invalid free. Why? Because we're trying to free the same memory twice. If we run like this, without Valgrind, then that crashes the program pretty much immediately, because we've figured out we have a double free. So when you run under Valgrind, as I was saying earlier, it's slightly more forgiving in that regard, in that if your program was going to crash before, it might not crash when it's being run under the supervision of Valgrind. It doesn't give you license to do bad things. Your program is running slower than it otherwise would. But it does give you an opportunity to catch the error and observe it, and see what additional information you have. Because when you get this second one where you have double free or corruption, and you get a core file, you got to open it up in the debugger. My impression is that most people aren't big fans of GDB. It's something you should try to learn to be comfortable with, to be able to debug your programs, but I understand it will probably never be your favorite debugger. But we have something a little helpful if we don't want to go into GDB here. When we look at the Valgrind output, because it says, well, the invalid free is the one that took place here at remove node when it was called from main on line 52. That's actually quite helpful. We can do something with that. I can look at that and I can say, oh, I'll go to line 52 and, I shouldn't have done a free there. Whereas that's much harder when we have to figure it out from looking at the core file and like backtrace how we got to where we are. So not as helpful. Okay, so that gives us some indication about some of the different kinds of memory error that we can encounter with Valgrind. If we compile this again and we run it again, now, we definitely have the memory that's lost, but it is fixable if we know what to do. We know where to look for where it was allocated. Now, still reachable kind of memory happens somewhat frequently when we are allocating something in main and we just don't deallocate it here before we get to the end. So that kind of thing is usually easier to fix than a memory leak. You can just remember to deallocate these things at the end of main. You have a valid pointer to it, so all you have to do is put that in, and our job is pretty much done. Okay, let's try looking at a couple of other programs that we have examined so far, the producer-consumer problem. Let's look at that one. So it spams with quite a lot of output, as we have previously discussed. Hopefully it tells us something useful. Yep, all the heap blocks were freed. I did a good job. What about a pthread program? Right. This is pthread 4 is the one that has problems counting. The sum is correct. Everything is fine in that one. Okay, let's try another one. All right. So in use at exit, 6,453 bytes and 64 blocks. This is not a program I have intentionally sabotaged for this purpose. This is just an example we did earlier in the course, so we need to find out what's wrong. So let's do it. I was better at typing. All right, let's find out. Okay, so we've got a bunch of blocks here that are leaked. Yeah, 40 bytes in this block, still reachable here. All of them look like they meet the criteria for it's not in our code, but we don't know that for sure. We have to try to rule that out. So, again, main at curl.c at line 20. That maybe gives us a hint as to where we're going to start looking. The rest of it looks suspiciously like this is a bug in libcurl NSS shared object 450, but we have to do a bit more investigation before we can jump to that conclusion. And if we go to line 20, we have a curl global init statement. And the question is, so did we allocate everything as we're supposed to? Did we use all the cleanups? Yeah, I mean, we did curl global cleanup. If I don't do curl global cleanup, just to demonstrate that. Right, yes, I have to add an additional argument when compiling curl. Usually there's a makefile for this. And let's see what Valgrind does with it now. Well, our situation got worse. If we go back to the previous invocation, it looks like curl global cleanup did clean up some, but there's some still reachable material in there. So, obviously, if I put here curl global cleanup, it does put our situation back where it was, but this is one of those examples where I'm not sure there's anything we can do about it. No, this is clearly something in the shared library, and we just have to sort of live with that and move on. If you were writing a report about it, if you've done the cleanup, you've cleaned up all the things that you can clean up, and you're still seeing, still reachable or memory leaks or things that are not in your code, then yeah, I mean, it's not your fault. So you would just, if you were writing a report, say in your report, well, I'm sorry, but this is a bug in the library and you should ignore it, and we would. So yeah, we've got at this point at least a little bit of an introduction to how to use Valgrind. As I say, it's a good idea to check your programs with this, because we will expect that, and we already check programs in the labs with them to make sure you don't leak any memory, so you should do the same. It is quite a powerful tool, but again, it's only capable of observing problems that are actually encountered at runtime. So if a block of code doesn't run because the test scenario that you were running under Valgrind doesn't execute that function, it doesn't happen. There's no way to make it. So the only way that you could actually check that out for sure is if you really did run your program, not exhaustively but extensively. Now, next thing we want to talk about is, well, Helgrind. So what is Helgrind? Helgrind is a similar idea to Valgrind, but the goal is to detect errors in the use of pthreads. And please enjoy this drawing of Helheim. So Helgrind is actually a pretty neat tool for improving performance when it comes down to it. Even though it doesn't actually do anything directly. When we take a single-threaded program, and we're trying to make it into a multi-threaded program or a multiple process kind of system, we're probably going to introduce errors, or at least the possibility thereof. Why is this? Some part of it is that humans are not super good at parallel thinking. Humans are sequential, so parallelism and concurrency remain difficult concepts for us. This is why you can't text and drive. Your brain might give you the illusion that you're able to do the two things at once, but not really. You are switching back and forth between them, and when you are operating a motor vehicle, that's dangerous to yourself as well as others on the road. So you got to be focused on the driving part if you don't want to hurt anybody. Now, the other part of that, the other component in the equation, is that languages like C and C++ were not designed with things like concurrency and synchronization in mind. And ultimately, the solution for this is, well, there's a way, but it's difficult, and it's up to you as the user to make sure that you do a good job. Yes, I mean, that can somewhat work, but it would actually be better if we considered that maybe we should use different tools that are better for this, that relieve some of the burden on you as the person who's programming it. But anyway, a program that is fast and wrong is much less likely to be useful than one that is slower but correct. So what we really want is to make the program both faster and keep it correct. That's the goal of Helgrind, is that after you've parallelized your code, determine where, if anywhere, there are concurrency problems. There's no way it can prove that your program is correct. That's incredibly difficult. It's a research problem on like static analysis about, can you analyze a program to identify problems at compile time? That's hard. Helgrind, like Valgrind, works only on what it sees. So it uses its observations of the behavior of the program and can identify concurrency problems. Can you think of any kinds of concurrency problems? Okay, we should be able to come up with at least one, but there are three categories that Helgrind uses to categorize errors, and they are as follows: misuse of the threads API, lock ordering problems, and data races. The first category really doesn't require a lot of explanation. These are programming errors that relate to the pthread API calls, and so if you unlock a mutex that is already unlocked, that will be reported as an error. If you deallocate mutex memory, even though the mutex was locked, that will be reported as an error. If a thread exits while holding onto a lock, again, that will be reported as an error. All those kinds of things are simple for Helgrind to observe. The second category of error, lock ordering problems, is something that we should know about already from our previous discussion of deadlock. That if you had a thread P that does a wait on A and then a wait on B, and then thread Q does a wait on B and then a wait on A, then that's a lock ordering problem because there is a risk of a deadlock. So, Helgrind is going to report that, and what it reports is, a lock ordering problem, and it does that by building a directed graph of lock acquisitions. So when a thread acquires a lock, Helgrind will check to see if a cycle exists. If so, it will say this is wrong. So Helgrind is not really capable of deciding what is the correct order. What it will do is will assume that the first order that it sees is correct. So if thread P runs first and it's lock A and then lock B, Helgrind will say, okay, from now on, I've built a directed graph that has one from A to B. It has an edge from A to B. And I will say that that is correct and any other order is incorrect. So the only other possible order in this case is B then A. Now it might be the case that in your program, A then B happens once, and B then A happens 99 times. Helgrind will be mad. It will report quite a lot of lock ordering errors as a result of this. However, it doesn't mean you have to change all of the B then A to be A then B. Because all that matters is consistency. The incorrect order just tells you about the problem. You could change either one of those. You could say first A, then B is the correct order, and you have to change 99 places, or you could say B, then A, and you have to change one place. As long as every thread does it consistently, everything is fine. And then, of course, there are data races. So I don't think I have to say anything about that. It is very clear, I think, what data races are by now. We're familiar with them. We've probably written some into our programs, hopefully unintentionally. But we know how those work, and we know how to deal with them. So how does Helgrind actually analyze data races, though? So the thing is that it's keeping track of the use of any of the concurrency mechanisms, like lock and unlock, signal, post, wait, that sort of thing. And anything that implies there might be an ordering between events is taken and added to a directic acyclic graph. And if memory is accessed between two different threads, and there's no ordering that it can determine based on this graph, it reports a race. Keeping in mind that at least one of the accesses has to be a write, because there is no such thing as reads conflicting with one another. So let's actually take it for a spin. All right, so once again, Professor Morton has contributed a file that's full of wonderful errors that we can look at, and we will do so. And to invoke Helgrind, we use at the command line Valgrind, but with this option tools is equal to Helgrind, and then the program that we want to run. Okay, oh boy, there's a lot of things to see. There's 7 errors from 7 different contexts. Now, one of the things that you can encounter is that you want to run Helgrind to detect data races, but you should actually check the program with Valgrind first. Because if there are a lot of memory errors and things going horribly wrong already with Valgrind, like with memcheck, then you probably want to address those first. And so for that reason, that's why Helgrind comes second in this discussion. But also, just as a general tip, if you wanted to analyze a given program, i.e. one that I'm not showing you as a demonstration, you would start with memcheck, and once you've got that under control, then you can move on to this. Okay, what have we got to look at? We'll go back up to the top, and this one is full of fun things. So there are thread announcements that appear in the output, and thread announcements are just like you would imagine. It is when a new thread is created, then you get notified of that, and you actually get some information about where the thread was created, so what function it was created in. And so for thread number 3, it was created in main at line 22, and thread number 2 was created in main at line 21. And that helps you sort of track down what thread is what. This is a very good indication, actually, of how these things are pretty much non-deterministic, and that the order in which threads run and the announcements that they make is totally arbitrary and may have nothing to do with the actual order in which they were created in the program. Because if we scroll down, we will find that there is an announcement for thread number 1, and that is the program's root thread. That's main. So the output that you get here is not necessarily sorted in any particular order, and it's not necessarily in some consistent order with respect to time. So yup, we just have to deal with that. Anyway, our thread announcements tell us what threads exist, and then we have some errors. So, possible data race during a write of size 4 at a memory address. If we know how to read memory addresses, it can give us a hint about was that stack allocated or heap allocated or something like that. But in this variable here by thread 3, it conflicts with a previous write of size 4 by thread number 2 in thread A. And in fact, if available, Helgrind will try to tell you what the variable name is if it knows it. So it says this address, this memory address is 0 bytes inside a variable named global. All right. Here is another thing that we discussed as a possibility. That is a lock ordering problem. And so lock order and then a hex address before another hex address is violated. The incorrect order happened when thread B tried to acquire the second lock here, followed by a later acquisition of the first lock in thread errors line 45. And it says the required order was established by thread A. If we ran this program again, we could get a different result where it would say actually, thread B did them in the correct order and thread A did them wrong. It just depends on which thread runs when. Okay. What are the locks? I mean, like, what are their names? It'll actually tell you something about that. It will say the lock at this address was first observed here, and it's 0 bytes inside data symbol mutex A. Okay, the 0 bytes part is wrong, but lock with hex address 6010C0 is mutex A, and 601080 is mutex B. This gives us actually a hint as to how does Helgrind think about locks. And the answer is by their memory address. If you remember from our discussion about how you could avoid deadlock by preventing a cycle in the resource allocation graph, one of the things that we needed was a unique identifier for resources. We said there exists a function f of ri, so it produces an integer that is associated with resource ri, which is then used to make a determination about whether it is greater than or less than some other number. Yeah, that's what happens here. It just so happens the implementation of this f of ri is the address of operator. Yep, that's how Helgrind thinks about these locks, and so it thinks about them by their memory address, and two locks can't be in the same location without being the same lock. Now, if you had two pointers to the same lock, it would be the same one, and therefore there's no possibility of some overlap. Every identifier is unique, and that's enough. It works. It gets the job done. It is straightforward. So that's how Helgrind will do it. So we can also see reported here exiting thread here still holds two locks. So when exit thread here runs, it still is holding on to things, so they should be unlocked before we do that. And it's thread number 3. We've already determined somewhat earlier on that thread B is up here, and in fact, by reading our output, we've made a determination that thread number 3, doing this lock in the wrong order, was thread B. We haven't even looked at the code, and we already know which thread is the offending thread. We have also a destroy of a locked mutex, which fails because, well, the device is in use. So you can call the destroy function, but it doesn't do what it's supposed to do. And then mutex destroy is called with an invalid argument. And those are our 7 errors. Okay, so I mean, what do we see? We have 2 mutex types up here, and we have some creation of those mutexes. We have creation of threads A and B, and then we destroy the mutexes. But actually, we destroy them wrong, because here on line 28 we have our first error. Copy paste error, very common. Could happen to anybody. You just copy and paste line 27 and you don't actually update it to destroy mutex B, and that's caught by Helgrind. Okay, thread A, lock mutex A, lock mutex B, then unlock them and sets global to be 1. Thread B does lock on B and lock on A in the wrong order and doesn't unlock them and then exits. So fixing the concurrency problems in this trivial example is pretty straightforward. I mean, we would move the global variable modifications inside a critical section. We would make the locks acquired in a consistent order. Choose A then B or B then A. It's up to you. we would make thread B unlock the mutexes when it's done, and then main should destroy the second mutex and not the first one 2 times. Okay, so yeah, the output from Helgrind makes it very easy actually to figure out what we need to do. So we just do it. But let's take a little bit more time to examine some of the other programs that we have worked on. So I'll point Helgrind at the curl program, even though you'll probably think it's, worthless. Okay, so here we got 0 errors from 0 contexts, but there's like suppressed 17 from 17. By default, whatever installation you have of Helgrind will know about some false positives, so it will choose to ignore that. We can actually ask for more details by running it with the -v option. And the -v option is super verbose, so it tells you all kinds of stuff, and it tells you about why it suppressed certain things. And it's like, well, I know that given what I've seen here, considering if this is a false positive, the blah blah, not super interesting, but it's there. Obviously, running Helgrind on like a single-threaded program doesn't give us anything very useful because there can't be that many concurrency errors, we hope, in a program that isn't concurrent. So let's try a different one. Let's try our producer-consumer problem. Okay, this produces quite a lot of output. If we scroll all the way back, we'll get to our thread announcements up here. And then it'll tell you these are the threads that were created, but hey. We're going to just wait for this to finish, and then we'll see what it says. As you will observe, it is definitely running slower than it runs when not being supervised by Helgrind. Because the normal version would be done by now. Okay, there were a mere 6,358,796 errors. Ouch. We're going to redirect the output of this because it'll help us to track down what's wrong. Okay. We still have our thread announcements, so a thread was created, whether it was created as a... Okay, and our first data race is something we can see here. It has to do with printf. Printf is going to cause a bunch of problems for us in this case because, in theory, printf is not super thread safe, but usually we can just bypass that and we can say it's fine. If you wanted to avoid these errors, you would add some mutex around print statements, and it would prevent this from happening and make sure you get things printed in a consistent order, but generally we are okay in that regard. It is, however, do we need to look for other data races? Yeah, here's one. So possible data race during read of size 4 at this index, the C index variable by thread 13, conflicting with a previous write of size 4 by thread 12. And if we open up the code, we'll find something is wrong there. And we also see such an error during a write of size 4 at this address by thread number 2, conflicting with another write by another thread. And this time it's buffer. So we got to look and see what's going on. And sure enough, what's happened here is that we have disabled the mutex lock and unlock around the shared variables here in the producer code and here again in the consumer code. So obviously this produces quite a lot of errors. We have lots of conflicting reads and writes. And so it tells us that like C-index and buffer, for example, are being manipulated in an unsafe way. We have a data race. Therefore, we know we should fix it. So let's put these back. And we'll see if that made things any better. We still have our printf problems. But things are looking a lot better. But again, it's quite a bit slower when we run it under Helgrind, same as Valgrind, and it has to monitor all these things and watch for locks and unlocks and everything. So it should not be surprising that it is quite slow. But hey, it will get done, and we'll see the result. Okay, so I skipped time ahead, so there wouldn't be quite as much, dead air without, some interstitial music or something, even though it would get me copyright strikes. Even if I hummed a tune that was moderately famous, I don't really have much of a singing voice. So yeah, we still have quite a lot of errors, but they're now all related to the, they're all now related to our, use of printf and those sorts of things. We can get around that. Let's do it. I swear if I was better at typing. Now, this isn't, as I say, strictly speaking, necessary, because it is quite possible that nothing really goes wrong and it's a false positive, but if you're tired of seeing that, you could do something to this effect. And let's try it out. Well, this is interesting. Attempt to lock a non-recursive lock, again, that I already hold. So at line 29, and consume, at consumer, line 57, lock was previously acquired. Here, consume 27. What's wrong? Well, Here's what's wrong. I did the wrong thing here. And locked, when it should have been unlocked. Maybe you were screaming that at your computer earlier. Whoops. Let's try again. Okay, and now, of course, everything has worked out. And no more errors. It just took a while, as you might have guessed from the time jump. Okay, that will do for our discussion today on the subject of Valgind and Helgrind. You should, at this point, have a reasonable understanding of how to use them and how to apply them to a problem that you're working on, to some code that you are writing. The important thing to remember is that whatever you're using, it just identifies the problem. It doesn't tell you the solution. So you have to figure out what variables are affected, you have to figure out how to prevent data races, you have to figure out where the deallocation is supposed to go, and you might find that frustrating. Like, if you ever work with somebody who's just a complainer, they never have any constructive suggestion, it's always like, this sucks, I don't like this, what about this, why doesn't this happen? You probably hate that person. So you might feel that way about Valgrind as you use it more and more. But ultimately, that's just a limitation of the tool. It can't solve the problem, but it can present to you enough information so that you can solve the problem. And that's a good sight better than we've been able to do up until now. So we should be happy about this. All right, we will leave off this topic now, and our next topic will take us back in time to Byzantium. See you then.